you, Vincent, for the introduction. Well, then I don't need to introduce myself anymore. So as you said, I'm Julien Gorenflot. I work oopala, in the ultra-fast dynamics group in the Solar Center in the King Abdullah University of Science and Technology in KAUST. And as you said, in there, I'm making selling organic photovoltaics mostly. So very happy to bring the NGSE seminar back to organic photovoltaics. And today I want to talk about transient absorption. And so TM means transient absorption. Uh, why we do it, how we do it, and also yeah, what it is actually. But just before talking about it, I wanted to talk about it. Maybe some of us know us a bit more for this. We've worked recently in figuring out what molecular energy levels can optimize the efficiency of organic solar cells. And there's plenty of really cool things for this. It's very, really exciting studies. And I really encourage you to check the presentation and Shafkat, who is now a professor in China, gave last year, as well as our latest updates that came early this year on this topic, which are mostly about the energetics, how you can choose your energy, molecular energies to optimize energy losses in organic solar cells. However, today I really wanted to talk about transient absorption. So none of this, just follow the links and please do it. It's really interesting topics. So transient absorption. Today I'm first gonna convince you how cool transient absorption is. And once you are convinced, I'm going to show you a bit more in detail what we do with it, what we use it for, and I choose this maybe uncommon approach, but to explain you really what and how it works transient absorption only after having made you sure you want to know. And I will conclude with the challenges we are facing currently in transient absorption spectroscopy. So the cool thing about transient absorptions, oh sorry for the animation, is that it can see everything and it can see all the time scale when you would like to see things. So for example, if you take a typical OPV active blend with an electron donor and an electron acceptor, and you shine a pulse of light on it, you're going to see using transient absorption that initially, right after excitation, you're going to form some excitons in your acceptor and also the electroabsorption of the excitons and in like hundreds of femtoseconds. And if you wait like 10 to 100 of picoseconds, you're going to see charges formed from those excitons. And if you wait even more until the charges start to decay, you're going to see some triplet states, triplet excitons from those Y2 material being formed in the nanosecond and plus scale. And what do I want to say? And you know that by probing really the absorption, each of those excited species has its specific spectral signature, and that's really what you use to probe all this at all those time scales. And so this is for the normalized version, but of course your data are the basics is not normalized, so you can also check the relative intensity of the signal, and it can hopefully tell you about the efficiency of the transfer between those different excited states. And that's very unique from TA. I mean, excitons you could see from the luminescence, charges by electric measurement, triplet maybe by the spin, but here I can see all of them at once. What I want to say, yeah, you probably know what is exciton. You of course know what are charges and triplets maybe also, but I may have lost you when I talk about electroabsorption. So just a small parenthesis. Electroabsorption, it's so when you have charges or electric field in your material, um, it's a signal that doesn't come from the charge themselves, but from the neutral molecules and not excited molecules which are between charges and that feel this electric field. And so what happens due to this electric field, the absorption spectrum of this neutral non-excited molecule is shifted. And so if you make the difference between um, its absorption with and without this field, which is equivalent to with and without the excitation, you obtain something which has this kind of spectral shape. And that's a feature that typically comes on top of the absorption features of the excited species, for example. And that's very interesting because to have it, you really need to have charges and already at a distance sufficient so that something not charged can be in between, and not too much so that your electric field can still be very intense. So that's been used by those guys, for example, to probe charge generation a while back. Anyway, back to my message about transient absorption. It is a really nice method. So now what do we want to do with it and how do we do it? Typically, we use transient absorption spectroscopy to probe the quantum efficiency of photocurrent generation in organic solar cells. And as you know, in organic solar cells, photocurrent generation has multiple steps, which involve multiple excited states. And so the quantum efficiency in the end is a product of the yield of all those steps. And we can actually see it from the evolution, transient evolution of the density of those states. So of course, the first step is absorption, which generates some excitons, and of course, you're probably going to have less excitons than what you had photons to start with. So that's your first yield. But as you know, those excitons need to diffuse to the heterojunction between the two semiconductors and some of them may not make it. Some of them may not make it. So when you see your charges generated, it also has a certain yield, charge transfer yield. Once you have those charges at the interface, the silicon-Becquerel bond, so to bring them away from each other, you may also lose some to generate recombination, and you will also see that from the evolution of your charge density. And finally, of course, the charges, once they're separated, they still need to be long enough to be extracted. And that would be your extraction yield. So that's really all the yield you can get from transient absorption. And as you can see, this graph here, it's really going to be our grail in our methodology. We try to get this graph. That's what we're doing. And to do that, we start with a sample which is basically your active layer, a bulk heterojunction on glass, not a full device. And you measure the transient absorption on it, which give you some spectra due to those excited species that evolve with time. And the next step, of course, is going to be to figure out who participate into the spectra and to isolate the individual contribution from, for example, here, charges and triplets, and to get the individual dynamics evolution of your excited species. Now the problem once you have here, that's the evolution of your signal, of your contribution, right, optical contribution. It doesn't tell you much unless you are able to convert that into charge or excited species density. So one way we do that is by comparing for charges, at least, by comparing with electrical measurements, also transient electrical measurements, such as the time delay collection field. Once we have when we have this transient charge density, that's where it becomes interesting, because there we can really parameterize this density with different models. And having the equation of those curves, we can simulate what it would be under a different illumination, and of course, typically one sun. And that's the result of it. So you can see it gives us all our yields. This is the same, but in equation instead of drawn. So that's the parameterized charge density, as the decay, not the generation. So why would we not be happy with this? Well, the problem is really where this information comes from. You want to simulate what happens under one sun, but what you shine on it's not really one sun, because first, the sun is not pulsed. Second, the sun is not monochromatic. Third, to see this signal, we typically use intensities from 10 to 100 of suns. And of course, the solar cell is a device, might behave quite differently than compared to our films where we're probing. So the question is, whatever we get here, is that real? Does it apply to solar cells? And to know more about it, we wanted to put our TA parameterized, decay charge densities into device simulations, and I will show you that it works, and that we can get some bonus features that we will not be able to get from TA alone or for device simulation alone. So back to TA. This is a TA sample, just glass, active layer on it, and yeah, air or vacuum most of the time. And of course, when you shine light on it, you just have a bare lamp below. You have an exponential decay of your light that it gets absorbed, but still rather simple. And because you don't have injection extraction, it's rather close to safe to assume that you have a homogeneous charge density. So of course, if you want to compare that with a device, the situation is very different because on device you have multiple layers, all in the thickness similar to your wavelengths. So you have a lot of interference effect. Your light in the device is very different. And your charge density is also very different because you can have extraction, maybe injection. So yeah, it's not as simple as a TID, but simulations can drift diffusion simulation can handle that. So they can of course simulate the charge densities. They can also include optical simulations that are going to simulate this interference pattern for all the wavelengths. So if you integrate over all the wavelengths, of course, you can get the generation rate through your active layer. So that's nice. And yeah, as I said, the simulation is going to simulate the recombinations generation. Those are the equations. You see them, you forget them. The important here is that you need a generation rate and a recombination rate. And for the generation rate, I already show you, we get it rather easily from the optical simulation. For the recombination rate, so we consider a non-geometric recombination proportional to the whole electron density and hole densities, which you also get from the simulation. What you miss is this prefactor. Now, on the other hand, what do we have from transient absorption? We have parameterized the transient decay of charge density. And one of the parts is geometric recombination, and that's basically going to happen to a certain fraction of your charges, no matter what. So all what this is just replaced by a fraction. Compared to your generation, you just multiply it by a separation efficiency, and that accounts for this part. Basically, this 1 minus f factor. Non-geometric recombination, so the recombination of separated charges, is a little bit more tricky because this behavior is equivalent to a recombination rate like this. So while this one is proportional to, you could say, the square of charge density if the charge density were equal, this one is proportional to the charge density to a different order with a different exponent. So, but we can make a square up here. Just then your prefactor becomes dependent on the charge density, which is not really a problem. So what we do, we first make a smart guess of what the charge density could reasonably be, and we estimate this prefactor, and then we launch a simulation, and we see a certain charge density which might be slightly different from the one we guessed because our smart guess was not so smart. But then we calculate the average charge density, and we calculate this prefactor for these new charge densities, and then we rerun simulation, give you another charge density from which we update the prefactor, and at some point it converges. So at some point, the charge density from the simulation becomes consistent with the one you're supposed to use there. So that works. And when we simulate devices using those information, we get this. So here you have experimental devices for comparison in the dashed lines, and the result of the simulation in full lines. And I took two extreme cases. So I told you the recombination prefactor depends on the charge density. So it means this recombination prefactor is not going to be the same when you are in an open circuit, when you accumulate a lot of charges because you don't extract them. And in the short circuit, when you extract a lot of charges, your charge density remains low. Here, I took very crude approximation to say that the prefactor was the same no matter which bias you apply, and I considered the prefactor considering large charge density, so like if you were in open circuit. And of course, because of that, you overestimate your K, so you overestimate your recombination. So you have a solar cell which is not exactly as good as a true one. On the other hand, if you take your prefactor considering a charge density, which is the one you have in short circuit, then you're going to underestimate your recombination. You're going to get a curve which is a bit better than the true one. It's going to give a bit more efficiency. But it was just to check the two most crude approximation. We can also choose something in between that will be more true. So yeah, so that works. Just as an indication, this one was a blend of a TQ1, a donor, a polymer donor, and PCBM. Yeah, exactly. So when we did that, basically we updated all our methodology to know not only what would happen in a transient situation with starting with a 1 cent pulse, but what really happens on a device in steady state under 1 cent. So that's pretty good, and it works. And the nice thing, of course, if you simulate a device, is that you can shut down one by one all the lost channels. And from your experimental current, this one was a pretty bad cells, but it's good for illustration. You can check which how much current density is lost to each loss mechanism separately. So that's a really, really convenient method. And then you can choose which one you want to address in priority, of course. Yeah, which is published there also in 2020. Exactly. Now, if you come back to all the protocol we've been following, you will remember that on the way to get the charge densities, we also found some overexcited species. In that case, triplet excitons. Um, and although they don't carry charge, they are here, and it would be interesting to know how much of them are here. First of all, out of curiosity. So similar to charge, the first step is to parameterize what the dynamics of those excitons. The thing is, for charge it's well studied, for triplets a bit less, and so we don't know if the rate equations that control the formation and the disappearance of these triplets are going to have an analytic solution. So rather than solving the evolution of triplet density, we stick directly to the evolution, to the derivative, time derivative of this triplet density. So this is a derivative. Anything positive means you are forming triplets. Anything negative means you are having triplets disappearing. Okay? And so we're trying to fit that. We tried, of course, different light intensities because uh, different phenomena may have different weights depending how intensively you excite. And because we didn't want to underweight the result from low light intensity, we normalized our decays. And so, yeah, so that's what we're going to try to fit. And we try different models. First model we consider maybe the triplets are formed upon charge recombination, but only the recombination of separated charges. And they decay due to reaching the end of the triplet lifetime. We try to fit this to the experimental rate. It doesn't work at all. It's just too slow. No, obviously, whatever happens is not that slow. So we try to speed it up and to make it more fluence dependent by adding a term of triplets annihilating with charges. Okay, and that helps a bit. That helps a bit. But if you look, for example, at the low density case, it's never getting positive. It's always negative. You cannot form. It looks like you cannot form triplets. Only make them disappearing, which doesn't make sense. So we need to put different models which will have more triplet generation. So to add that, we put triplets forming from recombination, but now all of the charge recombination, not only the separated charges, but also the charges that haven't managed to separate at the interface. And that helps. That does indeed speed up the formation of charges. And the last touch to make it even better is to replace this charge triplet annihilation by the triplet annihilation. And then we get a kind of decent fit of your triplet evolution. So that's nice. We have the rate equation governing our triplet densities. And from the simulation, we have the charge density on an operating device. So we could solve this equation in steady state by putting in the charge density that we get from an operating device. So this becomes zero, of course, because it's steady state. And when we do that, we get basically the triplet density on the device. And that's pretty cool because these triplets at the time were really overlooked. But when you look at it, and we still don't know what they do, but we know that there's kind of many of them. When you have short circuit current, there could be in most of the device more triplets than electrons, for example, a larger density of triplets. Yeah. Yeah, so that's it for this part. As I said, we combined transient absorption spectroscopy with device simulation, which showed us that the TA rates do make sense if you put them in device simulation, and they do give you the same result as what you see experimentally. And by doing that, you get really some bonus, which is something that can really not be probed by TA because it's steady state and too low excitation density, and cannot be probed, of course, by device because it's triplets, it's not charged, which is a triplet density on the device. So this was published there 3 years ago. Yeah. Well, okay, that's things that could be improved that we would be able to improve now is to implement the field dependence of charge generation also, as well as a more explicit charge density dependence of the recombination rate, which is also feasible now. Yeah. So I hope by now you know how powerful TA can be if it's used the right way. So now I'm gonna finally talk about what TA is a little bit, just a bit, because like 5 minutes. Yeah. So I told you this is the result of transient absorption, so some spectra. So where does it come from? So basically, transient absorption spectroscopy is an excited state spectroscopy. So first thing you do, you excite states. You start from a relaxed system and you pump it with some light to create some excited species. And then what you probe is what those excited species are. And you probe it optically because you want something that can probe very fast. So any transition that starts from there, you can probe. You can probe the absorption to higher excited states. You can probe the decay to lower excited state. But of course, because it's called transient absorption, mostly the most important is this one. And so let's do that. It's a differential method. So really what you're going to check is how different is your absorption once you have created this excited state compared to what it was without it. So what you do, you make this absorption spectra or transmission spectra of your film, and then you excite your film and you do it again and you monitor the difference. Like can you see, there's no difference. Because obviously you need to zoom a little bit and you need to zoom a little bit more. You are probing very small relative signal, typically 10 to the minus 3 to 10 to the minus 6 of the transmitted light. So there's a lot of averaging, there's a lot of techniques that make it work. It's not a fast technique, but it can access everything. Exactly. So yeah. So how to get this mode change is part of the trick. Um, and basically what you probe in this kind of transient absorption is a transition between the electronic levels. Over transition exists, but that's not what we probe here. And so you get some spectra, and I'm going to show you how they look like. Again, this is a simplified version of the experiment, excited sample, and probe light through it. And you can see different things. Your TS spectra will typically look like this, with some part positive, more transmission, and some part negative, less transmission through the sample. And they correspond to all those things. So the thing I mentioned before, this absorption from this excited state to over excited state occur at an energy which is different from what you have from the ground state. So it gives you some additional absorption figure. That's what we call the photon-induced absorption. That's important because this is really a signature of which kind of excited state you are here. Exciton will not have its photon-induced absorption at the same place in charge than a triplet, than the exciton of the other material. Another thing, when you have created your excited state, you have basically depleted your ground state. So by doing so, Well, obviously, there's less ground state. The ground state absorb less. So you have this positive feature because the ground state absorb less. So where the ground state used to absorb, you have more light going to your detector. And that's also a very important feature because it tells you where the excitation is. Like if you have a donor and acceptor, if your excitation is an acceptor, means you have depleted your ground state absorb ground state of the acceptor. So you will see this feature where the acceptor absorbs. While if your excitation is in the donor, then you're going to deplete your donor, and you're going to see this ground state bleach in the place where the donor used to absorb. And finally, last signal is from this x-axis state back to the ground state. You don't see fluorescence in transient absorption directly for technical reasons, but it can happen that a photon which is passing through your material is taking a photon together with him, and this is stimulated emission. And so you see that also on top of it in the PL region, but it's not photoluminescence. And that's also interesting because only excitons do that. So it also tells you about which material, which kind of excited species you have. And that's all I'll say about TA. I'm not going to go into details too much. For a last part, I'm just going to tell you about the current challenges. You may have noticed the paper I presented before. It's donor with a fullerene. So that's not the most up-to-date systems, and it was already not the most up-to-date when the paper went out 3 years ago, and there's a reason for this. Because we are facing two challenges, basically. Managing to figure out the dynamics of excited species, and the second is to understand them. So yeah, finding the dynamics. So really those steps from the spectra, managing to tell there is a contribution of triplets, there's a contribution of charges, there's a contribution of this and that. The problem in that step is that really, as I told you, triplets sees everything. And what you do in that step, you see your excited state spectra, you see at the beginning, you get the ones in blue, like if you probe right after exciting it. And if you wait more, you're going to get at the end the ones in red here. And you see it changes. It means there's several excited states. And what we do is we try to distribute that between the contribution of several excited species. We're trying to talk to the triplets, to the excitons. But the problem, you cannot talk to one. They all speak in the same time. They all speak in the same time because the signature of each of the species completely overlap all over the spectrum. So this is the four species I considered before. There's not any place when you can probe only one of them. And that's new with fullerene because with fullerene, typically whatever is a fullerene was kind of transparent. It has a very small contribution, so you could neglect it. So basically, you have your excitons of the donor and then the charges. Now everything is talking together. And when you can see from the dynamics is that everyone is talking at the same time also, not only spectrally, but temporally. So for any time delay here, there's no time delay when you will have only one contribution. There's always two, three. That's the easy case. If you add that you excite the donor, so you could have donor exciton on top of this. And actually, at the end, you don't get only triplets. At the moment, I'm trying to separate spectra in which you have 6 contributions. So yeah, it's a mess. And really, a tiny difference in your signature of one excited species make a big difference in your dynamics. Like for example, recently I had this triplet absorption, charge absorption look like this, nice, and I had the electro absorption feature on top of it. And I thought here it looked weird. Why it goes down and suddenly it goes up again? That's really weird. So I thought probably it's the true spectra looks more like this. Whatever my algorithm found something wrong. So I changed it to a different spectra, which made more sense to me. The problem, this has huge consequences on the dynamics. What you have to look here are the red part here. Those are the dynamics of the charges. So that's how it looks like if you consider those spectral signature. But if you consider the spectral signature actually like this, the dynamics of your charges are going to be like this, very different, very separated. And when you feed them later, this one will correspond to 54% of charge separation, but this one will correspond to only 30% of charge separation. And we did not even modify the charge spectra, right? We modified the electroabsorption spectrum. But you know, those things that used to be counted as charges here are maybe now counted as electroabsorption, so the charge density is different. And yeah, that's the kind of problem we're facing, really. So really the question is how to get good spectra, how to get more constraints also, so that your algorithm find a unique decomposition of your spectra into several components. Some possibility is to give more constraint, like force to have certain shape for your spectra. Like here, for example, you have an abrupt jump in your spectrum. There's not specific reason for that, so you could force these to look like a Gaussian, for example. It's limited, but it helps. And on the other side, you need more input. You need to have reference spectra for charges, for excitons, for triplets. You can also try to vary the temperature. Hopefully, if you decrease the temperature enough, all the things that happen in the same time going to become more and more sequential. So maybe you can find some area in which one excited species is really dominating. That's the hope. Anyway, you need more input, more parameters. Another help could be to apply some electric field to change the ratio of charge to excitons, for example. Things like this, but then you need to measure on device, which adds a lot of complexity too. Yeah, so that's for the problem of understanding what is what in your spectra. And the other problem, once you've managed to roughly understand what is your charge contribution, for example, is to understand what's going on. Because, for example, it used to be easy when an organic semiconductor absorbs some light, it forms some excitons, and it's going to need to diffuse the interface to make charges. When you excite a Y derivative, you immediately see some electroabsorption feature. And the whole community of spectroscopy is discussing what do we form in Y derivative, really? Do you form some charges? Are those excitons or charges? But then this electroabsorption has a different dynamic compared to the excitons. So we just don't know. That's for the short time scale. Once you put things in blend, of course, it gets even more funny. Once you recombine your charges, you expect normally to end up either with the triplet of whichever material has the lowest energy, or just even more easy, to the ground state. But what we see here, if you blend a Y derivative with PM6, or at least this one, Y2 with PM6, the final excited species somehow is bleaching both materials. So it has some donor and some acceptor. So is your final species a city state somehow? Or does your final species have actually two species but which are in equilibrium with each other? So the density decrease together, so you cannot make the difference because the dynamics are really the same. That's something to need to be figured out. So yeah, a lot of exciting things still to figure out. Oh, I just wanted to show why I don't explain the details of transient absorption. It's just because we don't really have time right now. But it's cheating. There's 4 setups on this table. But one is fairly complicated already. With that, I want to thank the people who participated to the first paper I presented. That's 2020, so most of the people are not here anymore. Shafkat is not doctor now, but he's professor. Yeah, and so on. Also, our collaborators from Linköping University are not in Linköping anymore. Martin is now in the University of Heidelberg, so close to you. And Amantas, I think, is in industry, if I don't make a mistake. But I still want to thank them, nevertheless, because it was a nice collaboration. Yeah, this is our current group, so we still plenty of people. This is a sun of chaos and some shade. This is just to say that transit absorption is cool. And what else do I want to say? Yeah, it's TA time. And there's some position open if I manage to motivate you to show you how cool it is. In Chemnitz, I went there to build a setup myself, so it's a setup that almost works. There's still a bit of fine tuning to do, but if you have a background of spectroscopy, not TA, but spectroscopy or OPV, feel free to apply to this to this funded PhD positions there. And yes, that's it for today. Now I'm waiting for questions.